So previously, we had seen double integrals that look like this. So integral sign 1 to 8, integral from 1 minus x squared, say, pretend, all the way to x to the fourth of, I don't know, x, y squared, dy, dx, something like this. And the thing to note is that the outermost integral here had to have fixed numbers. There had to be constants here. That was a requirement. Okay, constants, that was a must. The inner integral, the endpoints can involve, they don't have to, they could just be plain numbers too, but they can involve x. To be a little clearer, because we're doing a dy and x is going to appear later, you can use a later variable. You can use an outer variable like that. So now, what we're going to look at is, integral, let's say 1 to 8, integral 1 minus x squared, x to the fourth, integral, let's say x plus y to x squared plus y squared of the function x times y squared times z dz, dy, dx. Okay, so this kind of thing is now going to make sense. This makes sense. Let's comment for clarity, like this thing about constants and can involve x, right? So this right here, this outer one, the outsidemost integral, must have constants, just like before. Okay, so then the next integral inside, this is, by the way, going to be the dy integral. And when the dy integral is done, if it leaves some x's over, that's fine, because we're going to do the dx one last. So this inner integral right here, this, the next integral, in this example, we have a dy, right? This can use fixed numbers, like we were seeing with the box just a moment ago, or can use an outside variable. Can use the outer variable. In this example, that outer variable is x. Then the innermost integral, the inside integral, may use variables which are in outer integrals. Right? So can use y, can use x, can use either of these. So can use y and or x. And you see this here with both x plus y and x squared plus y squared. So as an interactive question, let's talk about why the rules should look like this. So I want you to please address the following. If this rule about which variable cannot appear in which integral is ignored. So let's pause, say what I mean here. We're seeing here that, say, the inner integral may use x, but it cannot use y or z, right? The outer integral must have constants. It cannot use x, y, or z. Let's say you tried. Let's say you did that. So if you ignored this rule, what issue would we have with the final answer? Perhaps the easiest way to address and answer this question is to go ahead and break the rules. Just instead of following the rules, break them intentionally, go through the integration process. It's going to seem a little strange, but then look at what your final answer is and then comment about what is wrong with that final answer. Okay, cool. I think that will help things out. And now, let's say that in the previous example, the one at the top of the screen, This would be the integral of a 3-input variable function, so f of x comma y comma z equals xy squared z, over the 3-dimensional region. So it won't be a box anymore, it'll be a different 3-dimensional region, which looks like this. Let's call it capital E. It'll be the set of all points x, y, z, satisfying the following. So first of all, x is always stuck between two constants, 1 and 8, and y will be stuck always between 1 minus x squared and x to the 4th, and z will always be stuck between x plus y and x squared plus y squared. Now, how would you do this integral? How would you evaluate this integral? I think this would be really essentially just exactly the way you'd expect, right? So you'd take this integral here, and since dz is on the inside, we should integrate with respect to z. Yeah, so we'd have copy the outer integral, copy the next outer integral. We're not ready for those yet. And then take a look at, let's see, integrate with respect to z. So x, y squared, z squared over 2, and we should evaluate this at z equals x squared plus y squared, and at x plus y, and then we're not ready yet for the dy dx, so we'll do that, right? Just to do one more step here, integral 1 to 8, integral 1 minus x squared to x to the 4th, let's see, x, y squared, x squared plus y squared quantity squared over 2 minus x, y squared, then x plus y quantity squared over 2 dy dz. Dy dx. So we'll pause here, just to say, we could continue this further, but you've got to square this and so on and so forth. So there's some work to do here, but at least now it's an integral. It's just a double integral now. And I think this is a good place to pause on this problem. I would just say that, generally speaking, the toughest part is not really doing the integral, is not doing or evaluating the integral. Okay, but writing E, whatever the region you're integrating over, in an inequality format. Like this we had there. That's, I think, what's challenging, right? So same kind of geometric issues going on, and this cascading thing of, one set of inequalities has to have just constants, then the next set of inequalities can mention the previous variable here, x, and then the last set of inequalities can mention all the variables. Now, we'll say that typically the toughest part is not doing the integral, but sometimes it is. So if an integral is tough, if it seems difficult to do, well, then maybe switch the order. Switch the order of integration. It really, in the end, technically requires a Fubini-like theorem, and technically the function you're integrating should be continuous, for instance, but let's not worry about that too much. Maybe, instead, you'll use polar. Okay? Or maybe you'll use something like polar. That thing will, just to preview what it's called, is called spherical coordinates.